In this module, we're going to go over data path. So the data path is how instructions get turned into actions by the computer. So we've gone over the MIPS instruction set. We've gone over the units or kind of gates that will take two inputs and produce an output depending on what kind of a gate it is. So we're going to talk about how the gates are put together to form a unit that will serve different functions. And then those functions will be to interpret the instruction and do whatever their instruction says, whether it's an add or load from memory or that. So the first thing we're going to go over is at a larger level how the data path and the items in it, the ALU, control unit, register file, interpret the 32-bit instruction. So recall this is from the first unit, but recall we want our CPU to perform well, and that's going to depend on the instruction count. So how many instructions does it take, and that's determined by the instruction set architecture and what kind of compiler you have. And it also is going to be determined by the cycle time. So, even if you can have lower the number of instructions, if you have a long cycle, it's going to take a longer time, and that's determined by the CPU hardware. And this week, we're talking about the CPU hardware. In the next 3 units, we're going to talk about actually 3 implementations of the MIPS. We're going to start this week with the single cycle version, where the instruction is read and interpreted, and hardware is used to cause the computer to do the action that the instruction wants, and it's going to all happen in one cycle. We're going to talk about multi-cycle next week. And then after that, we're going to talk about pipelined, where the instruction is broken up into into multiple cycles, where in each cycle part of the data path is run. But this week we're doing a single cycle where in one cycle the instruction is read and interpreted, and the computer takes an action in one cycle. We've talked about the MIPS instruction set. Actually, we are going to only talk about load and store word, some amount of the R types, branch, unequal, and jump. I mean, obviously there are a lot more. It would make our data path way more complicated. This is kind of enough to see the basics of how a data path is built. So recall what happens when we execute an instruction. The first thing that happens is there's a program counter. So that says, what is the address of the next instruction I want to execute. It's going to go to the instruction memory and fetch that instruction. Then, if it's an R type, it's going to read the register numbers that the instruction refers to. It's going to go to the register file and read those registers. Then it's going to use the values from the registers and the ALU to do whatever it is the ALU, whatever it is the instruction wants done. And we'll go over all the different, even in a load word and store word, ALU is used. Obviously in R type it's used. And then next, if it's a load or store kind of instruction, it's going to access data memory. And recall that only load and store access data memory. That's one of the RISC properties of MIPS. Then, if it's not a branch or jump, we're going to update the program counter and say go to the next instruction. And recall that addresses in MIPS are bytes, So the address is a byte. It's an address of a byte in memory. An instruction is 32 bits, and that's 4 bytes. So the next instruction is going to be 4 bytes later than the current one. So we update the program counter by adding 4 to it. So this is what happens when we execute an instruction. Now we're going to look at what kind of hardware do we need to make that happen. So here's an overview of the data path. You're going to be seeing a lot of this for the next few weeks. So take it in now. So these are all pieces of equipment, or units in our data path. This is a register with the program counter in it. So this is just going to give the unit the address of the instruction that it wants to execute. That address is going to travel over this path. And another thing to keep in mind when looking at these diagrams for the next few weeks, when we have a little item like this, that means this address is sent to 2 places. It's sent to here, to the instruction memory, and it's sent up to this little adding unit. So these little triangle-ish trapezoid things are adding units. So the address at the same time, in parallel, is sent to here and to here. So up here, we add 4 to the address. So this is where the program counter gets updated. At the same time, these 2 things are happening in parallel. The address is sent to the instruction memory. This signifies the instruction memory. So it sends the address, and then that address is fetched. The data at that address is fetched, and that would be the instruction, and the instruction comes out the other end of this unit. So out here is now the MIPS instruction, the 32 ones and zeros that we studied last week. Come out here. Now, so this is a 32-bit, 32 bits. Those fields we talked about, the opcode, register fields, shift amount, and function code. This, we'll talk about what this is, but it's actually what's going to happen if this is a branch or a jump. The information will get sent up here, and a different program counter will get calculated, but that'll become more clear as this lecture goes on. But anyway, so the 32 bits get sent here, and remember we have those fields with register numbers in them. So that gets sent here. Those 3 fields, that data gets sent here. In some instances, the lower 16 bits are a value. That'll get sent here. So at the same time, the bits fields that are registers, so how can I put this? So the 5 bits that represent a register get sent here, 5 bits that would represent a register get sent here, 5 bits that represent a register. At the same time, those lower 16 bits that could be getting sent here, they're also getting sent here. Just in case those lower 16 bits represent a number, they'll be sent here and go to the ALU. Out here comes those values from the registers. Okay, so we might need 2 registers from the values, like for an R type. So they'll come out here. At this point, we're going to talk about this. We're going to decide which value we need. And we'll talk about how that gets done. Here, the result from the ALU comes out. Whatever the instruction says we need to do, it's going to come out here. If this is a load or store word, what's going to come out here is going to be an address. And that'll go to the data memory. That'll either get loaded or stored. So it'll all become more clear, but just get an idea that there's an instruction going through here. And sometimes the same bits are getting sent to 2 places while we figure out what that data represents. We're going to send it everywhere it might need to go. So you'll notice here there's a couple places where there's two possibilities. So do we want this line to be PC plus 4, or do we want to come from the jump? So there's a choice here. Here, the choice is, do I want to write back data to a register because it was an R type, or do I want to write back data that came from data memory? And here, do I want to use a register as this lower value, or is this an immediate value? Because we talked about those immediate kind of operands. So there's two options for what can go to the ALU. So this is a choice too. So we add things called multiplexers at those points. And now here's like everything added in. Okay, so here's our multiplexers. So here we're going to send a signal. All these blue lines in here are control signals. The black is the instruction going through. The blue are control signals. So we're going to talk about how those control signals are generated, but they tell the data path what to do. So they're going to tell it what kind of operation, is it addition or subtraction that we're doing. They're going to tell it, are we going to take this immediate value, the lower 16 bits, or we're going to take a register value as our lower input? Are we branching? So should I take the branch address, or should I just take PC plus 4? So these control signals are telling the data path what to do, which data to use. That's the blue, and the black are the actual bits in the instruction. And we're going to go over all this as we go along. So again, we're talking about clock cycles, and actions happen on in clock intervals. So we're going to start with an instruction, and in one clock interval, all of the items from the data path are going to, all of the gates in there are going to have results, and the results are going to be determined all in one cycle through the whole data path. So we start with a state, which is the instruction going through. You know, we read an instruction, all that combinational logic happens, and then at the end, that instruction has been executed. And there's a new program counter. Okay, so we're going to go through the bits, the items in the data path one at a time. So we talked about this already. This is the first item we're going to talk about. So this is a register, and it's got a 32-bit address in it, which is where the instruction is we want to read. So that 32-bit address goes into the instruction memory. It goes to that address in memory and fetches the instruction, which is also 32 bits. So the instruction is, again, the thing that we studied a couple weeks ago or last week. That's 32 bits with the fields, the opcode, the register fields, the shift amount, and the function code. At the same time as we're reading the address, we're sending the program counter value up to this adder and adding 4 to it. Next thing we're going to do is look at this register file. So this is a set of, MIPS has 32 registers, so this is going to be register numbers, and their data values are in this file. So we're going to send in register values. So remember, we have register numbers between 0 and 32, or 0 and 31. This value is going to go in here. Remember, we have the R, S, R, T, R, D. And they're going to be values, and this register file is going to read it. It's going to read those bits that represent the RS, then go get that data. Whatever this number is, it's going to go to that value in the register file, or that address in the register file, read the data, and send it out. Same for either R, yeah, for RT or RD. There's several options for the second data value, but whichever one it is, that data is going to come out here. This is going to be data coming back, so if it's an R type, remember we have 3 registers, we're going to write a new value to the register, the RD. This is going to be the data we write, is going to come through here. And then this is a control value that we're going to talk about that's telling us, are we writing a register? Just yes or no. Do I have to pay attention to this input right here? And then this is the ALU, which we'll talk about. We're going to give it 2 values and get a result. And there's several operations that we can do. There's addition, subtraction, and or that we can do. And again, we're going to have these control values come in. There's a 4-bit control value that's going to come in and tell the ALU which of these operations do you want me to do. If we have a load or store operation, that's when the data memory comes into play. So this is our data memory. And we're going to pass in an address. And if it's a load word, we're going to go to that address, get the data, and send it out, and send it to a register. If it's a store word, we're going to go to that address and take the data that's coming in and put it and write it in that address in data memory. And this, again, are control units that are going to say, are we writing data? Yes or no. Are we reading data? Yes or no. Obviously, one of these is, they could both be 0, or one of them could be 1. We're either reading or writing or doing neither because it was an R type. And the sign extension unit, what this does, so if you remember, there's certain the I immediate instructions and the load and store word have the lower 16 bits are a value. For the load and store, that's an offset from the address. So we take the lower 16 bits and we just sign extend it to 32 bits. So we take whatever bit, the most significant bit, so this would be bits 15 to 0 in the instruction. We would take bit 15, whether it's a 1 or a 0, and just repeat it out to 32. So if you recall what happens in a branch instruction, BEQ is a branch on equal is going to take 2 register values and it's going to compare the values in these 2 registers, and if they are equal, there's a 16-bit value. The lower 16 bits are an immediate value, and it's going to increment the current program counter by this amount. So it's an offset to go to. So if these 2 are equal, jump the value that's in these lower 16 bits. And again, we're shifting left. So these 16 bits are the number of instructions to shift. So when we shift 2 places, that's shifting left 2. Shift left 2 is equivalent to multiplying something by 4. So if we take a value that's 0, 0, 1 and shift it left 2, it becomes 1, 0, 0. So it's just taking this 1 and shifting it left 2. That means 1 becomes 4. So we're saying, okay, so this is a word displacement. We want it to be a byte displacement because we do byte addressing, so we have to multiply it by 4. So in this operation, which still isn't quite complete yet, we take the lower 16 bits. So on a branch, we're going to take the lower 16 bits, send them to the sign extend unit, turn it into 32 bits, multiply it by 4 to get the number of bytes, and then add that to the current program counter +4 because that's actually how it works. And that's the new address we want to fetch next time. And then this ALU will determine if these two registers are equal. And then we're going to see some logic in a second. So where this is going to decide, oh, if that's a 0, then go to this address, and we'll see that shortly. And in this week, we're going to talk about a single cycle data path. So we're going to say this whole data path is going to be done in one cycle. So we do need separate instruction and data memories. And then we're going to use multiplexers to determine which source to use depending on the instruction. So this is our simple data path again, kind of all put together. Instruction comes in. We take these register fields, RS, RT, RD. We also send the lower 16 bits down to the sign extend unit just in case we need that. So actually there's the same data is going to both places, and these control units are going to tell it which data to use. So this is going to say, was this an R type, or is this something where I need this lower 16 bits? Do you want to do an AND, an OR, a addition, a subtraction? Are we doing a load or store word? Are we writing this data back to, so if it's a load word, are we writing this data back to a register? Yes or no? And actually, this is actually, if it's an R type, the result comes out here, and it actually goes through here and through the mux. And if it's R type, this mux will be set to 0 so that data can get written back. And even fuller, same idea. So we have the branch up here, and this is saying, are we branching or not? And so now we're going to look a little closer at the ALU and see how the control unit works. So how does it tell it what to do? So hopefully you've taken this in. Of course, if you have any questions, please let me know if I've gone too fast or not been clear. Anyway, that concludes this one. Stay tuned for more about the data path and the ALU and the control unit and everything fun.